Okay, I have a student request on some problems from the homework assignment. And the student requests were, sorry about the noise there, question 12.1, which I guess I can do here, question 12.1, and questions 12.12 and 1.3. She had more too, but I'm gonna deal with these in this video. First of all, why is there an upper limit to the photon energy? Hopefully you can see that from where you are. Why is there an upper limit to the photon energy that can be observed in the discrete emission spectrum of the hydrogen atom? All right, hydrogen atom. And so what I'm going to do, I'm thinking about this. I'm going to go through and let's see, upper limit to the photon energy, the emission spectrum. All right, so for the emission spectrum, we're talking about something that goes from an initial to a final, right? An energy level, initial, energy level, final. And in doing so, it lets off a photon of h nu, right? Of energy h nu. The formula that we got for that, this is the Bohr model. Bohr model. Can you read my writing? The formula that we used for that was, there's the, let's see, the frequency in reciprocal centimeters is equal to the Rydberg constant in reciprocal centimeters over, or rather times, the difference between, I don't even know how to say this, reciprocal, final, initial, squared, and whatever. Okay? Now, looking into this in a little more depth, let's think about this. Why is there an upper limit to the photon energy that can be observed from the emission spectrum? Okay, so first of all, when are we going to get a photon from an excited, let's picture this. Here's the nucleus of a hydrogen atom. And here's N is equal to 1, or let's say final. Let's see, it's going to be coming down here, okay? And N is equal to N initial. Okay, so if there's an upper limit, picture what would happen if there were no upper limit of this. What would be required for no upper limit? That would be if you had some N is equal to something really big, right? Really, really big. Actually, if there's no upper limit, that means that N initial can be bigger and bigger and bigger and bigger, and it can fall all the way back down. Okay? So what happens if N is really, really big? Let's say N initial is equal to infinity, and N final is equal to 1. That is, N initial is as far away from the hydrogen nucleus as it can get. I think I'm off camera here, aren't I? N initial is, let's say it's, I'm not sure if my notation here is good, okay? N initial is really big. It's as far away from the nucleus as it can get. And N final, let's say, is 1. Okay, that would be really big. Okay? Let's put that into here. Actually, I'm going to let you guys do that. Put infinity into this equation and 1 into this equation in the appropriate places. And then go back and look at this and answer the question, why is there an upper limit to the photon energy? So I realize I've just given you a hint. And the hint, I haven't actually come out and said the answer. But the hint is, what would it take for there not to be an upper limit to a photon energy that can be observed in the emission spectrum of the hydrogen atom? Okay, feel free to bring that question to class, but I really want to take you there instead of just giving you the answer. Okay, so that's 12.1. Hints at 12.1. I'm only going to give you hints at all three of these, I think. Number 12.2, or 12.12. Why is a diffraction pattern generated by an electron gun formed by electrons interfering with themselves only, rather than with one another? First of all, I'll tell you, I don't really agree with this. It's a statement made by Engel and Reid. It's on page 301. I'm giving you a hint again, and I want you to figure it out, okay? Page 301. It's the second paragraph. You bring that sentence to me. Bring the sentence that indicates why a diffraction pattern generated by an electron gun formed by electrons interfering with themselves only. That's the big deal right there. with themselves rather than with one another. And I think there's one sentence that's going to answer that question. Okay, that's on page 301. I think I already wrote that there, second paragraph. Okay, now what about 1213? How can data from photoelectric effect experiments be used to obtain numerical values for Planck's constant H? I like this question. All right, so first of all, what's the photoelectric effect is described with the equation: the kinetic energy of the electron is equal to h nu minus phi, which is the work function. Okay? I'm only going to give you a hint here also. First of all, what are the variables that we have here? There's only two variables. You know, that's question number one. What are the variables? I wish I could... What are the variables? Matter of fact, I'm going to force you to pause the video here before I tell you. Pause the video and tell me, what are the variables? Okay, I'm going to pretend that you paused it. I hope you did. And let me point out that the variables are here. First of all, this is not a variable, right? Why? Because that's Planck's, watch this, constant. So that's not a variable. Okay? What else is not a variable? Boom. That's the work function. And any particular metal that you're working with is going to have a characteristic work function. Okay? So the two variables are the energy of the kinetic energy of the emitted electron and the frequency of the incoming photon. All right, now that we know that, I'm going to give you one last hint here, and I think I'm going to delay this answer also, and that is this. Look, if we've got two variables, y is equal to mx plus b, what we can do, here's the answer. What we can do is we can vary the frequency of the incoming photon, measure the kinetic energy of the emitted electrons, and graph them. Graph. Oh, I love math. Graph them. And after we've graphed them, by the way, what kind of relationship are you expecting? Do you see that this has the same form as this? Do you see that this has the form of this? Do you recognize this? What's its name? It's the general form of a linear equation. Right? It's just a line. So with our graph, what kind of a curve are we expecting? We're expecting a line. What's the slope going to be? It's going to be Planck's constant. Good. Okay, hope that's helpful. I realize I did not answer all of these questions, but my feeling is that that's going to be helpful to you as you think about these things. Send me more questions.